In this video, I'm going to talk about how to use echoice2, my new package for choice modeling. So let's say you've already installed the package successfully. Then you should first of all load it in order to be able to use it. So you just click on it in the package tab in RStudio. And when you click on it, it will open up the help file. So here we can actually get help for each of the functions that are part of the package, and we can also head over to the vignette. We can head to the HTML version, which is easy to read, and there's a lot of explanation in here that you should work through if you want to work with the package. One more thing I like to do is I also like to load the entire tidyverse. The way I've set the dependencies, I'm more specific about which packages are actually necessary, but loading the entire tidyverse gives me a little bit extra flexibility because this package integrates nicely with the entire tidyverse, and you can then use predictions and aggregate and summarize them in whatever way you want or is necessary for your problem. Okay, so we've loaded the package. We've also loaded the tidyverse. Let's clear the console and work through the example set forth in the package. So what do we need to know about how the package is organized? So everything that's for discrete demand starts in DD. Everything that's for volumetric demand starts in VD. And then everything that's universal starts in EC for echoice. And this makes it easy to find the right function for your purpose. Also keep in mind that you can use autocomplete. So if you type dd underscore in the console in the editor, you see that the tooltip here gives you all the functions that start in dd underscore, which makes it really easy to find the function that you actually need. So then the estimation functions continue in EST, the demand simulators continue in DEM, and then other utility functions are named accordingly. A lot of them will be EC, so for discrete and volumetric demand, some might be specific to either discrete or volumetric demand. Okay, so in this vignette, I just have a simple volumetric demand model example. What is also really important about this package is how data is organized. So let's actually get to that example to illustrate the point. So here we have data from an ice cream volumetric conjoint experiment. And here you can see actually the data structure. So let's actually copy over these commands here so we can actually see it live. So I'm loading the ice cream data set from the package with a data function, and then let's take a look inside. The first column is ID. That's a custom ID or respondent ID. That basically just tracks the individual. Then you have task that identifies a choice occasion. So it could be a choice task if it's in conjoint, or like a purchase incidence or choice occasion if you are in if you have transaction data. And then alt for alternative tracks the choice alternatives. Then we have the quantity demanded as X, P for price, and then the remaining columns are the attributes describing each of these choice alternatives. So as you can see, this is a long format, so sort of a tidyverse style data organization. And that makes it very, very versatile. So each individual can have a different number of choice tasks, and each choice task can contain a different number of choice alternatives, which makes it super flexible and easy to apply to transaction data, not just conjoint data, where the dimensions are much more constrained, and typically all the responses have the same number of choice tasks. But that's obviously not the case if you look at actual demand at a store. For now, I'm only looking at categorical attributes like you have in conjoint very often, but of course continuous attributes I will talk about later, and that will be added to the package later to actually treat them separately and automatically based on their scale level. For now, again, I'm only looking at categorical attributes. So here we have brand, flavor, and size. So yeah, this is again tidyverse style data. You can also pre-process the data. You can keep holdout portions of the data very easily just using simple dplyr commands. I have a helper function here that's ec summarize attribute levels, and that gives me a quick overview of the different levels of the factors that are my attributes. So you can see which brands are included, which flavors are included, and which sizes are available. It helps me to work with a new data set rather quickly. And the next thing here in the vignette is just to create a plot that just does a little bit more descriptive analysis to the data and giving you a histogram of the choice quantities in the data set. Notice there's nothing that's specific to my package here. This is just standard tidyverse syntax, and that's the main point of this package, to actually have a data structure that you can naturally use with tidyverse commands, and then you can just pipe it into any of the estimation or demand prediction functions without having to rearrange the data. The package does it for you. In this section, I'm generating a holdout per portion of the data. So I'm actually generating a seed here for consistency, and then I'm basically splitting the data into a calibration and a holdout portion. And again, I'm just using standard tidyverse syntax to do so. There's nothing that's specific to this package doing so. And this is, again, making it very versatile because you can use your existing tidyverse knowledge to do any of these things. Then to estimate, and this is from the package, we're using a standard volumetric demand model, so VDS, VDM for standard volumetric demand model. I'm just generating 20,000 draws here to make it really fast, but of course you should at least use 100,000 draws, ideally even more than that. So let's actually estimate this. In this virtual machine I have 8 cores, so it's going to use these 8 cores to run the estimation. And it should be done in just a little bit. So then if you want to work with the output, so ice cream est will contain the draws. So if you take a look at its structure, you can see, well, it has a lot of attributes that I use to store information. But the first few objects are actually the draws, so the individual theta draws, mu draws, the upper level draws, basically sigma draws, so upper level covariance, tracking the log likelihood, and a couple other things. You can directly work with that if you like, but I have utility functions that help you to work with it. So EC estimates mu will summarize the upper level and basically give you the attribute, the level, like a parameter name. It gives you posterior mean, posterior standard deviation, a credibility interval, tells you whether it's significant, and it adds more meta information just in case you want to run different models and compare them. You can simply stack these upper level summaries and then compare them quite easily. Yeah, so model diagnostics, so you can generate a trace plot of the upper level parameters quite easily. So this is using ggplot for visualization. Of course, you can also skip that and directly generate your plots if you like. In order to assess fit, LMD for now is just a very simple harmonic mean estimation or approximation. So use ECLMD-NR to do that. It splits the draws into 4 parts, so you can also see if it's converged. Here it is, and you see what the marginal likelihood is like. A little bit more interesting is a holdout fit. And so let's generate holdout demand first. So how do we do that? So holdout demand is, well, the holdout portion of the ice cream data. Prep new prediction ensures that the factor levels match the original data, so the calibration portion of the data. So it will just make sure that the order of the factor levels is correctly set, so that the design matrices are automatically created in the same fashion. And then we use the demand simulator for the standard volumetric demand model. I'm also thinning the draws and throwing away the burn-in from the draws in the estimation object. So that runs rather fast. And then let's just take a look at what HO, so holdout demand, looks like. So basically just looks like the demand data that we have, only that it's just the holdout portion. And then the draws, the posterior draws of demand, are in a column called .dem draws, which is kind of nice. So there are 501 draws of the posterior of demand, and they're stored just in one cell. And then using per, it's very easy to summarize that. But I have utility functions that do it for you, but they are just internally using per, the popular package these days that makes it really easy to work with data like this. So one utility function I have is ecdem eval, so that just evaluates the fit and for the holdout with MSE, MAE, shows you the bias and the relative absolute error. So basically just compares X to each of the DEM draws, computes the MSE and MAE and so on for each of the draws, and then averages it. So it's a posterior mean estimate of these holdout fit statistics. Yeah, and what else can you do with a package? So you can do a little bit of policy simulation if you want, or market simulation if you want to call it that. So here I'm generating a very simple scenario. And then using prep new prediction, I'm making sure that the factor levels match the original data. So if I'm looking at my scenario now, you see that it's the same structure as before: ID, task, alternative, price, and then brand, flavor, and size are factors, and the factor levels are in the same order as the original data because I used the prep new prediction function. So that's very important, because if the order is not in order, then the design matrix would not be correctly created. Let's then use a setting here. So there are just 10 offerings in this simulated market. Let's just apply that to all of the respondents. So let's take a look at my market. So now we have 3,000 rows. So basically we have 10 offerings for each of the 300 respondents in the data set. That's why we have 3,000 rows in this market. In order to simulate choices, what do? We use, again, VDM, so the choice simulator for the standard volumetric demand model. I'm telling it where the draws are, and I'm using this this market definition. So then in this new object called my market demand, I again have the market that I had before, but I have an added column here that's .dem draws that contains, again, the posterior draws of demand. And then I can aggregate them and summarize them. So let's first look at an aggregation. So here, basically, I have demand draws for each individual task and alternative combination, but maybe I just want to know, basically, for each product, so for each brand, flavor, size combination, what's going to be the aggregate demand, so the demand for all the 300 respondents taken together. So that's what I'm obtaining with ecdem aggregate, and I'm just telling it which variables to use for aggregation. So here I'm using brand, flavor, and size. And then probably I want to know what is the posterior mean of demand. So I'm just adding an ecdem summarize in order to get these posterior summaries. And so now I know, okay, Häagen-Dazs chocolate, 14.6 units will probably be sold to these 300 respondents taken together. There's a little bit more in here on how to generate demand curves, but I'm going to leave it at this for the short video introduction showing how my package works. So again, the biggest point is to make it really easy to work with choice models, to have this data structure that's very flexible, to have a very compact extra column that contains all the draws that lets you summarize and aggregate in whatever way you want using standard tidyverse commands. That's the main point here, and additional features and models will be added over time.